I have observed that it's not the 15th of July. In my defense, when I compiled these slides this morning, it was the 15th of July in Pittsburgh. Okay, so this talk is not hopefully self-contained, but very much a move in an ongoing literature discussion, which is, I think, going to come up at other points in this meeting as well, about this so-called Gibbs versus Boltzmann distinction in how statistical mechanics is thought about. And the title is a reference to, you might say, an answer to this recent characteristically interesting paper by Roman Frigg and Charlotte Verndl. Can somebody please say what Gibbsian statistical mechanics says? And in the paper, they say the following. They say GSM, Gibbsian statistical mechanics, of course, is widely used and considered by many to be the theory of statistical mechanics. Yes, a closer look at GSM reveals that it is unclear what the theory says and how it bears on experimental practice. Hence our plea, can someone please say what GSM says? Sure. So here's what I'm going to do in this talk. I'm going to say what I take to be the formulation of Gibbsian statistical mechanics in the sense that they're referring to or was relevant to this discussion. And I'll come back to what I mean by that in a moment. Then I'm going to talk about what the concerns are that Frigg and Verndl raised about this. I'll talk about the way in which they see there as a conceptual mismatch between Gibbsian statistical mechanics and thermodynamics. I'll talk about the way in which they see the way in which fluctuation phenomena are handled in statistical mechanics as key to somehow reconciling that mismatch. And I'll mention the way in which they see that as being at most something that can be done for a certain subclass of systems. Then I'll talk about what I want to call statistical thermodynamics, which I take to be the way of understanding thermodynamics, which is natural from that Gibbsian statistical mechanical point of view, and which is such that if you understand thermodynamics that way, the mismatch that Frigg and Verndl discussed goes away. And then I'll finish by looping back to fluctuations and saying some things about how to think about fluctuations, and through that, how to think about the probabilities that come up in Gibbsian statistical mechanics in ways that perhaps have some interest in their own right over and above their relevance to this discussion. I'll say as a kind of caveat beforehand, so there's a kind of way the literature runs that often identifies Gibbsian statistical mechanics with what Gibbs said, and Boltzmannian statistical mechanics with what Boltzmann said. And there's also an idea that somehow this is an internal and ongoing and current dispute within physics, within the mainstream application of statistical mechanics. So I want to dispute both of those claims. So in the first place, I'm pretty persuaded by, particularly by Wayne, that both the historical Gibbs and the historical Boltzmann said many things that are salient to both what people seem to mean now by Boltzmannian statistical mechanics and what people mean but now by Boltzmannian statistical mechanics. So, my use of these terms is conventional. It shouldn't be taken as any reference to what was said historically by Gibbs and Boltzmann. This isn't going to be a history talk. The second point is that all I mean by Gibbsian statistical mechanics in that point of view is how mainstream theoretical physics uses statistical mechanics. There's obviously a certain space for variation there, and it depends a little bit which community you talk about, but in my general experience, there is an overwhelming consensus on the general calculational technology of statistical mechanics within mainstream physics. And the Boltzmann versus Gibbs framework is something between a kind of philosophical construction that's sometimes informative, but not capturing an internal debate among physicists, or insofar as there is such a debate, then it's a small heterodox position in the main shape of statistical mechanics. And I could say that I think that issue about philosophers glomming on very strongly to a small heterodox position in physics is not unique to this particular example. It turns out you can make a good living by defending the controversial view that what makes physicists think about a given topic is broadly along the right lines. Okay, let me get going on that project. So here's the setup I want to say for Gibbsian statistical mechanics. I want to say the setup is characterized by a system, which in turn mathematically is going to be characterized by a state space and a Hamiltonian, a statistical state, and I'm being intentionally ambiguous here between classical and quantum throughout. By statistical state, I'll lay the cards on the table a little. I mean either a probability measure over a state space that is a phase space, or a density operator on a state space that is a Hilbert space. A dynamics, the rate of change of that statistical state is its bracket with the Hamiltonian, where the bracket is either Poisson bracket or minus IH bar times the commutator, or plus IH bar times the commutator, depending on your sign convention. There's a correct sign convention in this case, I just can't remember it. I was told that the difference between a good and a bad theoretical physicist is whether the number of sign errors you make is odd or even. And an expectation rule, which gives the expectation value, which for the moment, let's think about purely formally. By definition, the expectation value is this linear functional of state and observable, and where again, you can read that thing fairly literally if you're thinking classically, or as an abbreviation for trace if you're thinking quantum mechanics. I'm probably mostly going to talk classically in this talk, but as much as possible, I'll try to stay neutral between those frameworks. Okay, what do we do with that machinery? As stated, that's just purely formal, but it gives us a dynamics, and we can ask things about that dynamics. And in particular, we can ask how the notion of equilibrium plays out under those dynamics. And we can identify a couple of notions of equilibrium. The first notion is what you might call exact statistical equilibrium. So the system in statistical equilibrium is for all of the dynamical variables are invariant under time. And a particular example of exact statistical equilibrium is the system might be an exact canonical equilibrium, which is to say all the expectation values of all the dynamical variables equal their expectation values, not just with regard to any old time invariant distribution, but the specific time invariant distribution that is the canonical distribution, i.e. e to the minus b to the Hamiltonian up to normalization. Okay, there's a number of important things you can say about either of those notions of equilibrium. In many ways, the most important thing to say about them is if you don't start them, then you won't get into them, at least not if the system's really evolving under the dynamics we gave. As everyone knows in this room, I didn't explain the details here, non-equilibrium states don't evolve to equilibrium states. There's lots of ways of seeing this. The quickest and most straightforward is to say that by definition, none of the features of equilibrium states change over time. That runs forward and backwards in time. So if it's true, then they can't have been away from equilibrium for some earlier time. So in practice, we do something different. There are a bunch of, shall I admit people if they, yeah. There are a bunch of different approaches here, but the dominant approach that gets taken in physics literature is to say, never mind exact statistical equilibrium, let's talk about statistical macroequilibrium. Let's pick a particular specific subset of dynamical variables, our favorite dynamical variables, our friends, which typically will be something like either for a system of very large number of degrees of freedom, something like the n particle marginals for observables on some subset of particles n that's much smaller than the total set. Or if I'm thinking my system extended in space, it might be that my observables average over some region, small compared to the overall extent of the system, but large compared to the individual constituents in the system. One or other of those, quite capacious, but nonetheless very small compared to the total set of observables, class of observables, we'll take that to be time invariant. And if that happens, we'll say the system is at statistical macroequilibrium. And again, as a strengthening that, we'll say the system is at canonical macroequilibrium if the expectation values of that same set of macro variables is fixed, not just with regard to any old station distribution, but or distribution that's macro stationary, but specifically the canonical distribution. And those notions, of course, systems can enter and exit. It's perfectly possible for a system to begin away from canonical macroequilibrium, evolve to canonical macroequilibrium, hang around at canonical macroequilibrium, and maybe even evolve back away from canonical macroequilibrium at some later time. Okay, so continuing for the moment, just to state what I take to be the content of this theory as it's used in physics, without making much attempt to defend or justify it. Once you have the Gibbsian machinery in play, you have a recipe that can be used to derive thermodynamics. Now, what do I mean by derive thermodynamics? Maybe I can send the slide. Let me say a moment about that before I say it in detail. I don't mean by that, at least not directly, derive thermodynamics in the sense of derive the qualitative content of the laws of thermodynamics, derive the claim that systems equilibrate, derive the abstract notion of an entropy function. In practice, in application, thermodynamics systems are characterized by their equation of state, by the expression of the entropy in terms of the energy and the other variables, or if you prefer, the energy in terms of the entropy of the other variables. Different systems have different equations of state. The main thing we're doing in the process we call deriving thermodynamics from Gibbsian statistical mechanics here in application in physics is working out what the equation of state is, usually under some approximation scheme, from the Hamiltonian of the system. And here's how that derivation goes. For mechanical variables, things like energy and particle number, we identify the thermodynamic values of those variables with their expectation values at canonical equilibrium. For other thermodynamic variables, like entropy and temperature, we identify them as certain other functions of the canonical distribution. For most famously, we identify the thermodynamic entropy with the Gibbs entropy or von Neumann entropy in quantum mechanics of the canonical distribution. And then, having done that, we have a mathematical expression that will tell us what the mathematical relation is between the thus identified thermodynamics. And the approach, if you want to ignore thinking about the foundations and shut up and calculate, goes something like this. Start with the Hamiltonian of the system, write down the formula that tells you the thermodynamic variables under these identifications, calculate the actual numerical values of those using some brilliant approximation scheme, proceed to Stockholm. So that's the formal framework. That's what's being done in statistical mechanics, in Gibbsian statistical mechanics. Now, Frigg and Vernal know that, of course. They're not when they say tell us what it says, they don't just mean repeating that recipe. Here's why they think whatever the formal success of this, there's something deeply conceptually problematic about all of this. So they take the purely formal structure I've written and write down a substantive contentful claim they take to be what's doing the work here. They say, they call this principle AP, translating it a little into the terminology I've just used. They say AP is when I'm measuring property F on a system in thermodynamic equilibrium, the observed equilibrium property of the value of the property is the ensemble average of the ensemble in statistical equilibrium. So you can see that, if you like, as the substantive content of the claim I was just describing in my formal algorithm a moment previously. Then you can think about this, although Frigg and Vernal don't require this, sort of in the sense of a Nagel-style bridge law reduction between theories. I've got my statistical mechanical theory of its various concepts. I've got my thermodynamic theory of its various concepts. Just as a matter of logical semantics, I can't literally derive one from the other without some kind of intertranslation of vocabulary. The intertranslation of vocabulary I'm going to give is the AP principle here. This wouldn't by itself suffice, but it's sufficient to raise the concerns there. And then they ask, like, how are we to make sense of that principle, how to use it? Perhaps actually, before I mention bare probabilism, let me say their starting point of concern here. Their starting concern is something like this, that thermodynamics, as they see it, is a theory that describes the actually occurrent properties of a system. The Gibbsian notions are notions of statistical averages over many measurements of a system or probabilistic features of the system. These are fundamentally conceptually different. They say something like the notion of thermodynamic equilibrium, i.e. all the actually possessed values of the macro quantities are constant in time, and the notion of statistical equilibrium, i.e. all the expectation values of the quantities are constant in time. Those are not just conceptually distinct, they don't even have the same extension. And so they ask the kind of question like, how then are we going to justify AP and under what circumstances? What's our way of understanding, if you like, interpreting that formal machinery that I just cashed out in such a way that would make AP legitimated? or in principle allow us to do without AP. And they essay a bunch of possibilities, most of which I'm not going to talk about. I mean, perhaps one that's worth mentioning briefly. They consider an older idea that, which you still find in some textbooks, that the route between this involves an identification of time averages and statistical averages. So there's a well-known argument that says, if I have a system that is ergodic, that is, makes its way through every point in phase space allowed by conserved quantities, and if my measurements on the system are on timescales long enough that it does in fact explore all or most of the system during that, then it's going to follow, well, then let me do then 2 steps. Firstly, it's going to follow just from the ergodicity that if I time average over a sufficiently long time, I'll get the same number as I would have got by taking the probabilistic expectation value. And secondly, in some sense, maybe if my actual measurements take long enough, I can identify them as these intervals. There were well-known objections to that. I won't rehearse them. I agree with Bergen-Verndl that that isn't viable. The version I want to discuss, which they bring up as a position that they don't ultimately think is viable, is bare probabilism, which they cash out, this is paraphrased mostly as follows, that the quantitative content of statistical mechanics is exhausted by the statistics of observables. And they quote me, in fact, as saying, saying statistical mechanics should not be thought of wholly or even primarily as itself a foundational project. But I think this is a quote from there. Sorry, the quote within is them quoting me, so this is a little bit Ouroboros, I suppose. On such a view, Gibbsian statistical mechanics really is just the study of the statistical properties of the distribution with nothing else added. According to bare probabilism, AP is superfluous and should be abandoned. And here's the full version of the quote I was getting at. The fact that they want to say that in defense of the claim has to be abandoned, in defense of the claim that on bare probabilism there is no prospect of deriving thermodynamics from statistical mechanics, they say the fact that thermodynamic equilibrium and statistical equilibrium are both equilibria does not mean that they are somehow similar, or that statistical equilibrium can serve as a stand-in for thermodynamic equilibrium when the latter is sized. In fact, apologies for repeating myself, it's from jet lag, statistical and thermodynamic equilibrium are not only conceptually distinct, the two notions do not have the same extension. An ensemble in statistical equilibrium not only contains systems at thermodynamic equilibrium, it can also contain systems that are not. And although they put this very sharply and precisely, they're reiterating concerns that have been raised largely from a Boltzmannian position about the way in which Gibbsian statistical mechanics could relate to thermodynamics that have been coming and going in the philosophy of physics literature for at least the last 30 years. I say Boltzmannian advisedly. The notion of equilibrium that I think Frigg and Verndl are assuming, and that they more explicitly defend in other places, is the Boltzmannian notion of equilibrium, where we can say, given again a collection of macro variables, so again something like n body observables for n much smaller than the size of the system, or spatial averages over appropriate size regions, given a collection of macro variables like that, we can define a microstate of a classical system as being Boltzmann equilibrium if the value of the macro variables, the actually possessed value of the macro variables, is time invariant, perhaps up to some small fluctuation. Presumably, it's never going to be literally exactly time invariant unless we literally define these things as some kind of discrete binning, but it's going to be such that the fluctuations are extremely small. They're good enough for government. And they define thermodynamic equilibrium as Boltzmannian. And I certainly agree with them under that definition. There can't be any idea of exceptionlessly establishing the validity of the link from Gibbsian statistical mechanics to thermodynamics I sketched earlier, because it will absolutely be the case that for some systems, even though they're at Gibbsian equilibrium, they won't be a Boltzmannian equilibrium in the sense. A classic example will be something like the individual Brownian pollen grain, which evolves such that its probabilistic description is given by the Boltzmann distribution, but which under a choice of macro variable where the location of the pollen grain counts as a macro variable is manifestly not a Boltzmann. Okay, so then they go on to ask, okay, how could this all be justified in the right circumstances? Because they're not stupid. They don't reject the fact the actual empirical success of the formula for many systems in the development of 20th, 21st century physics So they say, and this is fairly standard, define the fluctuation of a system with some microstate with respect to some macro variable as the difference between its actual value and the equilibrium distribution. So some points will have the actual equilibrium value and therefore will have zero fluctuation. Some will have fluctuated above it, some will have fluctuated. And their suggestion is that AP would be justified as a good approximation of any system where the probability of large fluctuation is zero. In other words, if it's the case that the fluctuations are small or nearly always small, that would suffice to explain why we can identify the Boltzmannian equilibrium value of the quantity with the thing we calculated. And they say systems with this character are systems that have thermodynamic fluctuations. They suggest the following. Firstly, they suggest that we should change the bare probabilism idea to qualified probabilism, which is something like we should add AP as a requirement of intertheoretic reduction. In other words, we need some additional assumptions such that with those assumptions plus bare probabilism, we'll ensure that AP holds whenever Gibbsian statistical mechanics is used in tandem. And that would identify a subclass of systems where the Gibbsian recipe would work, and then presumably we would hope or look for arguments as to why we're dealing with the subclass in the actual empirically successful case. Alternatively, they suggest instead of qualified probabilism, we could have fluctuation probabilism, which is a restriction on Gibbsian statistical mechanics itself. So the idea here is something like we shouldn't even do Gibbsian statistical mechanics except for the systems that have thermodynamic fluctuations. The difference between those two might be somewhat semantic, at least for the purposes of doing thermodynamics via Gibbsian statistical mechanics. They're going to have the same conclusion, which is only those systems with small thermodynamic fluctuations, with thermodynamic fluctuations, i.e. fluctuations at equilibrium that are small, are going to be those to which the recipe is just. And then I should say their worry is that these are substantive, non-trivial constraints, and we are not at all confident when, if at all, they're going to apply. Okay, so what they have in place here, if you like, is a sort of irenic compromise, consilience strategy where somehow we can give up on some aspects of the Gibbsian framework and incorporate some other important aspects, incorporate some aspects of different frameworks, and reach a kind of pluralist stability. Okay, I want to be much more uncontested than that. I don't want to give up anything at all. I want to continue defending the unqualified validity of Gibbsian statistical mechanics as a theory in itself and as a foundation for thermodynamics. And my basis for doing that is to disagree with Frigg and Berndl, though we'll see how much that's a substantive disagreement rather than terminology in a moment, as to what we should mean, not as a matter of history, but in the 21st century, as to what thermodynamics is. And I want to say that what we should mean by thermodynamics in contemporary physics, and what I think most working physicists do mean by thermodynamics in contemporary physics, is something we might call statistical thermodynamics. And in statistical thermodynamics, even when doing thermodynamics, all quantities are to be interpreted as statistical or probabilistic features. So when in thermodynamics we refer to a thermodynamic property of a system, we're always referring to some kind of statistical property. Or to be a little more careful, and here I'm borrowing a distinction that Wayne was kind enough to bring to my attention, we can do a tripartite distinction of thermodynamic variables into those that are associated directly with macroscopic features of the microstate, those that are associated more indirectly with the thermodynamic features of the system, and those which describe external constraints on the system. The first of those categories, which include things like particle number, energy, magnetic field in some cases, angular momentum, those quantities are, when you see them thermodynamically, you should always read them as an expectation. The second set of quantities, when you see them thermodynamically, you should always read them as collective, non-expectation property, not of the microstate of the system, but of the probability distribution over the microstates. And the third set of parameters no one thinks you should read statistically. Those are externally imposed constraints that you're modeling as some kind of parameter in the system. And on that basis, I want to say there is a categorical thermodynamics which you can think of as a kind of, if you like, a limiting case or a theory derivable from statistical thermodynamics. In categorical thermodynamics, we assume that the quantities actually are actual possessed values, but categorical thermodynamics only ever hold in certain cases through kind of law of large numbers type considerations. And it's not clear to me that it even makes sense in an historical context to think of categorical thermodynamics as a substantively different theory rather than just a useful approximative regime for statistical thermodynamics, insofar as those are even. Okay, so why do I think that's the right way to read contemporary physics? Well, here's the shape of the conversation, if you like. I'm not 100% sure how to answer for that. It seems completely manifest if you read any piece of careful physics work in sort of practical statistical mechanics in the last half century. But Frigg and Verndl draw exactly the opposite conclusion, and they're careful about how to think about it. They say about 2/3 of the about 30 textbooks on statistical mechanics we consulted when researching this article offer explicit statements of AP, which, if you remember, is the principle that the actual measured value on any given measurement of the system coincides with the expectation value derived from the Gibbsian method. And those that do not explicitly state AP appeal to it tacitly by basing their considerations on that. So notice that AP, as we've seen, is not compatible with the unqualified reduction of thermodynamics, statistical mechanics, and so is in disagreement with my statistical thermodynamics. In statistical thermodynamics, the average value you get, the expected value of the measurement you make in thermodynamics equals the Gibbsian expectation value, but there's no guarantee that the actual value will equal the Gibbsian expectation. So how do we pursue this? So I looked a little bit at some of the examples here and found the following, that part of what's going on is there are two subtly different averaging principles, and it's not a very straightforward task to see exactly what is meant by textbooks. So here's AP, the principle that Frigg and Verndl adopt. Here's a principle we could call AP star, which is the much more minimal thing I said that is definitional of statistical thermodynamics, which is just that the thermodynamic quantities are identified. So the thermodynamic quantities in the theory are formal terms in the structure of the theory. The way in which those quantities are related to concrete experiments is to some extent up for grabs. According to statistical thermodynamics, it's indeed true that thermodynamic quantities are identified with expectation values. And then given their expectation values, then of course the way you measure those quantities requires the normal techniques of statistics and probability theory. According to Frigg and Verndl, the principle that's being assumed in the textbooks is that the actual and the principle they state explicitly in the paper is that the actual measured value of the quantity corresponds to the expectation value. Okay, so how do we resolve that? I mean, so it looks like there's probably not much option here, but to say, well, it's 30 texts, let's just work through how we do for time. So I've got about an hour, including questions. So if we do one per 2 minutes and drop the question period, it's probably doable. Let's not do that. Here's a different route to say why I think it's hard not to recognize that that statistical reading of thermodynamics is tacit or explicit in at least a vast swathe of the contemporary. I want to give 3 examples of programs in contemporary statistical mechanics, work that's been influential over the last, well, in one case, the last 40 or 50 years, in the other 2 cases in the 21st century, which claim unambiguously have to be understood in terms of statistical reading of them. So the first example of that is the Landauer-Bennett approach to exorcising Maxwell's demon. So again, in this audience, I won't describe that in a lot of detail. Landauer said, and Bennett developed and popularized the ideas that the way to understand Maxwell's demon involved realizing that the entropy cost of erasing the demon, the information gathered by the demon, inevitably cancelled out, or at least cancelled out the entropy gain from the demon using its information to manipulate the system in ways that lower local temperature. More generally, the idea is something like I can use information to manipulate a system. If I have that information, it's a genuine thermodynamic resource. But if I want to keep getting that information, I need to keep collecting it. And if I'm operating with a fixed memory, I need to keep erasing it. The erasure comes with a cost. That position is highly controversial in contemporary philosophy of physics. Notwithstanding the views of my esteemed colleague John Norton, I think the position is broadly correct. But I'm not going to argue for that here, because my point isn't that the Landau-Bennett approach is correct. It's the Landau-Bennett approach has been extremely influential in physics and manifestly requires the statistical reading of thermodynamics. And you can see this, for instance, in the way in which Landau and Bennett talk about examples of single molecule gases and the way in which they derive claims that are manifestly claims that hold an expectation. Second example, we've already had some discussion of, I think we'll probably have more, the whole modern theory of fluctuation of thermodynamics, beginning with the Jasinski equality and the Crookes fluctuation theorem that in some ways grounds and generalizes it. So to only briefly reprise, because we've already had a presentation of it, the Jasinski starts with the thermodynamic inequality that expected work, the expected work to do a transformation is going to be at least as large as the change of free energy, and derives it as a consequence of a strict equality that the expected value of eta minus beta of the work equals e to the minus beta of the free energy difference. This has had an incredible amount of influence on the subject, been led to many experimental tests, enormous theoretical work, gets called out in at least one Nobel Prize. Manifestly and obviously, it's using a statistical conception of thermodynamics. You just read that directly off the map. The literal thing that Jasinski writes down for the form of the second law he's using is an expectation. I won't go over the details here because, again, Eugene's talk taken us through it. And the third, which also came up in Eugene's talk, is, I guess it's close to, but not quite in Eugene's talk, is the single shot program in quantum thermodynamics. So the idea of the single shot program is thermodynamics is generally saying things about how you could transform one system to another, what kind of transformations you can bring about, given certain thermodynamic resources. This is the resource theory of thermodynamics. I've called it the control theory. Those are essentially the same idea. Under this notion, I want to see, can I bring about a transformation of this kind, between this kind of system and that kind? And whether I can or not depends what resources I have available to do it. And the whole starting point of the single shot program is standard thermodynamic claims are expressed as expectation value claims. Can we go beyond that? Can we say, not just can we bring about this kind of transformation on average, but can we bring it about every time? And it's immediate and manifest from that statement of it that the starting point they have for what the standard results of thermodynamics are results in expectation. Okay, so again, I'm not defending here any of these programs as well-motivated or correct, but they are profoundly influential. I mean, see the paper for the relevant citation lists. I don't think there's any serious space to disagree that these have been among the most, perhaps the single shot program is newer and it's less clear, but the first two of these have been among the most influential sets of ideas in the last half century of theoretical statistical mechanics. And they all require the statistical interpretation. So I conclude from that, and I was talking to Wayne about this earlier, there's always a little bit of a flow back and forth between normative and descriptive when saying what the mainstream position in physics is. Physics is always a bit inchoate, and there's a matter of what you put together. And so at least to some extent, you can take this as a sort of defense and apologia for the statistical reading of thermodynamics. But I want to claim that those collections of examples suffice to show at least the extremely widespread presence in very influential parts of the literature of a explicitly statistical reading of thermodynamics. And that explicitly statistical reading of thermodynamics is derivable exceptionlessly, or at least there's no bar to deriving exceptionlessly from the Gibbsian notion of statistics and statistical evidence. Okay, let me, the last part of the talk, move on to this issue of fluctuations. Because after all, Frigg and Wernbel are concerned that insofar as we have this bare probabilism reading of what's going on, we just don't have any very good connection between the numbers that come through in thermodynamics and the actual things we might measure in the lab. So, well, perhaps let me hash out how the fluctuation story is supposed to go for the bare probabilism account. So we want to suppose a system is prepared in statistical equilibrium. Here are some questions we can ask about it. Perhaps I should say, just as a warm-up to this, part of Frigg and Verndel's concern is something like the following. They want to say, how can I relate the supposed statistics of this distribution to what I measure in the lab? And their route through this is something like, maybe I measure the system many, many times. If I do measure it many, many times, will I reproduce the Gibbsian distribution or not? And they take it as kind of a requirement of the process that I should reproduce it for Gibbsian statistical mechanics to work. And they're concerned that there are very substantive assumptions going on to make it true that what happens if I measure the system many, many times is that I match what I get statistically. I'll loop back to a bit more detail about what they're saying in a moment. But let me first say how statements about these statistical results, these probability distributions over measurements, play out on the bare probabilist view. So some questions we can ask. Firstly, I prepare the system at statistical equilibrium. I allow it to evolve over time, either under its isolated dynamics or in contact with a heat bath, if that's the way I've got it set up, but in any case, such that it counts as remaining at equilibrium. If I measure the system at some later time, is the probability distribution over that measurement given by rho? Yes, that's the bare probabilist. Second question. If it's measured at many later times, is the probability distribution over any one of those measurements given by rho? Yes, says the bare probabilist. If I measure it at many later times, is the joint probability distribution over all of those measurements given by a product of rho? Maybe, says the bare probabilist, only if the measurements are uncorrelated. The bare probabilist is saying no more and no less than the probability distribution over the system state at time t is given by rho. If I want to know the two-time probability distribution over pairs of measurements made at one time and made at another time, simply knowing rho doesn't suffice to answer that question. But I don't simply know rho according to the Gibbsian framework. I also know the Hamiltonian. And it's a mathematically statable and in principle, and in practice approximately, and if you're lucky, possible to calculate that inside that machine. And when you calculate that two-time or more generally multi-time result, maybe you'll find the outcomes are correlated, or maybe you won't. There's no commitment in the bare probabilist framework to say that they will be, but if they are uncorrelated, then yes, the statistics will reproduce the probability distribution. If they are correlated, it won't. If they're uncorrelated, if we want to measure the distribution, if we want to test, for instance, the claim that at equilibrium, the system's macro variables are described canonically, well, if the system's measurements are uncorrelated, then we can do that by measuring one system many, many times. If we can't, we'll just have to pair many, many systems at equilibrium and measure them all. So that's just something that the Gibbsian framework just accepts. It's not anything that's rejected there. And in fact, these kind of multi-time correlations are highly important in various bits of non-equilibrium, near equilibrium statistical mechanics. Here's Frigg and Verndel's concerns in a bit more detail. Can we really be confident that correlations disappear quickly in systems we probe with repeated measurements? Can we really be confident that repeated preparation of a system prepares it at statistical equilibrium? If the first isn't true, we won't be able to empirically access these distributions by multiple samplings. But don't we, they say, often in fact have systems where we think multiple samplings will indeed return these statistics? And secondly, if the way we're supposed to measure it in the absence of that is to prepare lots of copies of the system and measure them, that only works if we're preparing the systems at statistical equilibrium. And how can we be confident that we do? I think that's the quick thing to say here is that in either case, this is just a concern that the system doesn't equilibrate or doesn't equilibrate quickly enough. To go in reverse order, what's my method for preparing a system at statistical equilibrium? It's to prepare the system in any old state and wait a bit. And provided a bit, can be specified as long compared to the relaxation time, then by definition, the system's distribution will be, well, at least with regard to the macro variables, will be the equilibrium distribution. And if we make sure we wait a bit between each measurement, where again, a bit means longer than the relaxation time, long compared to the relaxation time, then again, the correlational data will be erased by the process of relaxation, and we'll get the right answer. If it isn't, we won't. So, in a sense, the concerns that Frigg and Vernal raise are just the concerns about how do we know that systems equilibrate and equilibrate on appropriate timescales. And of course, the answer is we don't. The problem of equilibration is a very deep problem in statistical mechanics and in the foundation of statistical mechanics, but nobody's disputing that, and nobody's claiming it's a special problem for the Gibbsian. It's not a problem to characterize what we mean by equilibration. We mean to evolve to a distribution that's macro equivalent to the canonical distribution. It's not difficult to characterize what we mean by the relaxation time. We mean something like that the difference in expectation between the expected, if you'll get delicately, well, let me do it this way, something like an appropriate norm between the actual distribution over macro properties and the equilibrium distribution tends off exponentially, and the relaxation time is the denominator in the exponent. We know what these notions mean. Can we prove in generality they happen? No, of course not. Do we know a lot about equilibration, both in general context and particular systems? Yes, we know a lot. But in any case, the general fact that a full understanding of equilibrium remains a central open problem in statistical mechanics doesn't obviate the fact that one can appeal to the notion of equilibrium in understanding what's going on conceptually in this framework. So I conclude from that that the account given by fluctuations by the Gibbsian account here is fully satisfactory. It gives us a perfectly good way of operationalizing the meaning of the distribution. It gives us a perfectly good way of understanding when it is that systems will or will not return that distribution through multi-time measurements of the systems. And it's worth saying, incidentally, again, appealing back to some of the more recent work here, that the process of sampling these distributions by measuring many copies of the system prepared at equilibrium and looking at the statistics is exactly what's going on in the experimental tests of Jasinski's equality and similar results in fluctuation thermodynamics. In other words, these days, if perhaps not in the mid-20th century, the details of this distribution, this idea of pairing systems many times and measuring them, is not a kind of thought experiment to make sense of the framework. It's actual cutting-edge experimenting. So to wrap up, the Gibbsian probability distribution is indeed the statistical state of the system. It determines the probability distribution over the expectation value of any variables for the system, and that includes the multi-time. Thermodynamics itself is itself fundamentally statistical, and categorical thermodynamics is just a limited case. And that's what Gibbsian statistical mechanics is. Thank you.
Well, that's yes, I just wonder what would they say about fluctuations in general? Whether the Boltzmannian framework can be applied to the fluctuating regime, or just like you restrict the domain of applicability and you think that thermodynamics and Boltzmannian thermodynamics only apply to the categorical, the limiting case.
Yeah, so there's a radical version of Boltzmannianism, which is helpful as a kind of position to consider, even if it's not completely clear if anyone's quite that radical. The radical Boltzmannian eschews all talk of probability. And for the radical Boltzmannian, all the thermodynamic contexts, and sometimes even all the statistical mechanical contexts, are always things we can get at only in the limit where fluctuations can be ignored. Something like the typicality approaches that get used in some of the sort of Rutgers style way of doing Boltzmannian statistical mechanics come relatively close to this framework. So they look to replace a quantitative notion of probability with a more qualitative notion. Insofar as one systematically issues probability in these frameworks, then I think that breed of Boltzmannian has a serious, probably fatal problem in reconciling the position with the manifest use of probabilistic technology across huge swathes of statistical mechanics. And to be honest, we don't really need to look at cool recent stuff on fluctuation thermodynamics to know that. We can go all the way back to Einstein and Brownian motion. The people who talk about typicality understand this, and when you push them on this, they will generally go over to large systems and say, well, what we really mean is something like the statistics of many, many copies system. I think that's okay, but the thing to say about that is, well, in the first place, you're not really rejecting probability here. You're just applying a frequentist to counter probability that has its strengths and weaknesses, but it's not really the rejection of probability. And secondly, and slightly more acerbically, weren't you the guys who just a few papers ago were railing against the very idea of the ensemble as a completely unscientific concept to introduce? That applies to the Boltzmann who tries to reject probabilistic notions entirely. It doesn't apply to Frigg and Thurman, or indeed to David Albert, who are perfectly happy to have some notion of probability in play. And at that point, and this is where to some extent there are perhaps indeed relatively ironic things to say. The Boltzmannian can say something like, fluctuations are fluctuations around Boltzmannian equilibrium. And taken thus far, the Gibbsian can agree with that. If you like, there are two notions of equilibrium in play. There's Boltzmannian equilibrium. Does the system in fact have the expected value of properties at the moment? And there's Gibbsian canonical equilibrium, is the system's probability distribution given by this distribution. From that point of view, things that are fluctuations around Boltzmannian equilibrium are fluctuations at Gibbsian equilibrium. And that can indeed just be a terminological disagreement.
Thank you.
Yeah, thank you. This reminds me of a question I wanted to ask, and this is a question as much for people in the audience, given that there are people in the audience who have more familiarity with the literature on the intertheory relations than I do. So how should we describe the relation? Actually, in the literature, is there terminology for the relation between statistical thermodynamics and categorical thermodynamics? Because it's kind of interesting because you don't, so categorical thermodynamics ascribes categorical properties to things. What you get from statistical thermodynamics is for certain kinds of systems, for the law of large numbers, with high probability, the actual value will be very close to that, to the expectation value, which is the value ascribed by categorical thermodynamics. Nagel wants us to deduce a limiting theory from the underlying theory, but what you're not. This is a different relation. Has there been discussion of this relation in the literature on the inner theory phase? So the question is for Jos and Patricia, and well, you if you want.
Yeah, I'll take advantage of me speaking, have a first go at it, and then let other people have a go. I mean, my take on this would be, and this is totally anachronistic, simply from the point of view of the contemporary physics, that statistical thermodynamics isn't in any way something that reduces to or has any kind of reduction relation with equilibrium statistical mechanics. It's simply the resource theory of equilibrium statistical mechanics. So to paraphrase Owen Moronian, this quote, statistical thermodynamics applies to any system of any size, and it is exact. And then, although neither of these theories are dynamical theories, then categorical thermodynamics does bear some kind of reduction or instantiation relation to statistical thermodynamics, in the sense that categorical thermodynamics is a purported resource theory for systems that describes not how their statistical properties are related, but how their actual categorical properties are related. Strictly and literally, that theory is false. However, it is approximately true with high probability for a certain class of systems, largely the large ones with small correlations. And that relation probably is going to fit into the broad space of intertheoretic relations, although I'm not committed here to any particular way of cashing that out.
Yeah, I guess I had a very similar question instead of an answer. So in that paper, if I remember correctly, they said that Gibbsian statistical mechanics is an effective theory of Boltzmann statistical mechanics, and they try to define an inter-theory relation in which Gibbsian statistical mechanics could be considered even a limiting case of Boltzmannian statistical mechanics. I wonder whether you're proposing something different here, or actually the opposite, or what would be the relation between Boltzmann and statistical mechanics?
Yeah, so they don't actually say that in that paper, but you're right that at least Charlotte, and it might well be joint work with Roman, has argued for that effective field theory reading in other places. But yes, I mean, without saying why I think they're wrong there, and indeed my position is more or less the opposite. But the Boltzmannian framework works, and in defense of that claim, and this goes a little bit to Joss's point, quite apart from anything else, there's the abstract generality of the Gibbsian framework as against the much more specific and detailed systems characterized by the Boltzmannian framework. I mean, again, something like the Brownian pollen grain, it's not obvious that the macrostate concept is even useful there. The notion of Boltzmannian equilibration is certainly not useful there. And yet that system is quantitatively very well described by Gibbsian StatMech technology.
Just a comment on what Patricia said. Maybe you, David, can comment on that. I think the reason why they say that Boltzmannian statistical mechanics is more fundamental and Gibbsian statistical mechanics is effective is because in Boltzmannian statistical mechanics, you have a clear ontology, right? You have this defined state, whereas in Gibbsian statistical mechanics, you have the probability distribution is indeed the statistical state of the system. So that's why they consider it to be effective. Yeah. So maybe you can comment on that.
Yeah, good. Thank you. That's very helpful. So there's a fundamental divide between approaches in philosophy of physics, between those who prioritize a clear ontology and those who prioritize empirical adequacy. I'm in the second camp, very unapologetically. There are lots of, I mean, the theory we have, we should get as clear as possible about it. And it's logically the case that if it were in fact logically impossible to get clear on a theory, and then perhaps that would tell us that the theory was ultimately unsound, even if it looked empirically correct and there'd be some way around it. However, the mere fact that one has a theory with a clear ontology is of zero value unless the theory succeeds in reproducing all the myriad empirical data we have, or at least look as if it's on a glide path to doing it, or at least in reproducing the success of the theories that do reproduce that data insofar as they reproduce it. I mean, classical mechanics has an extremely clear ontology. The theory that nothing exists has an even clearer ontology. Neither of those is a satisfactory scientific theory because both of them get the answers wrong in vast numbers of spaces where we have other theories that get the answers right. But there are, you can see that methodological dispute cutting right the way through philosophy of physics. I mean, I could talk about Bow, and the analogy is probably fairly obvious. I could talk about AQFT.
Yeah. Oh, you have a follow-up, but you have a question as well, so you can just second.
Okay. Yeah, I guess they're related, and they're basically following up on the question that was just asked. And as someone who wants to have their cake and eat it too with respect to those two options that you just laid out. Yeah, I was wondering what you think the statistical state is ontologically. And I was sort of interpreting the Frigg-Verndl. One way of interpreting the question is, give me an account of that state. And of course, there are many options. Like it could be a physical chance, it could be a credence, it could be, a third option, epistemic chance or something like that. But I was imagining that those would generate different understandings of the physical theory of GSM. And then there would be interesting questions about which one of those is preferable to which others, that kind of thing. Do you have any views on that?
No, sure. So, I mean, just as a matter of Frigg-Verndl exegesis, whether or not that concern is in the back of their mind, it's not something that's particularly foregrounded in this paper. But it's a perfectly legitimate concern. I mean, to be clear, when I say I prefer empirical adequacy to ontological clarity, I don't mean that we shouldn't seek clarity. I mean, our starting point should be empirically adequate theories, and then we should seek to understand those theories, and we should treat replacing them with other theories, however clear, as an absolute last resort. But yes, so it's absolutely, I'd identify as one of the key philosophical problems for statistical mechanics is to make sense of the probabilities that appear in StatMech. I mean, this is off topic of things I've talked about here, but to comment on it briefly, I think we need to get some kind of understanding of those probabilities in a way that treats them as quasi-objective, in the sense that there are robust things we can say about those distributions that seem to be true, testable, measurable. There's then a bunch of strategies you can have to do that, but I think getting that in some way is just a success criterion, given the fact we use this concept. For what it's worth, I think they are quantum mechanical probabilities in the semi-classical limit, the decoherent limit, and so we can go over to quantum mechanics to ask what's the origins of quantum probabilities. And if you want to know what are the origins of quantum probabilities, I've got a story to tell you. But I haven't defended that here at all, and my reasons for that are somewhat independent. Wayne has a theory that I find quite plausible in classical physics, but I'm more skeptical whether it applies in our universe.
Yeah, I just want to make a comment with the question of ontology is, I mean, at least in classical statistical mechanics, ask what is the ontology? It's precisely the same. We are talking about whatever, if I make a categorical statement about molecules, and then I make a probabilistically qualified statement about molecules, I haven't changed the subject. Like, weather forecasters used to make categorical predictions. Now they make probabilistic predictions, but they're not talking about different things. So it is not a shift in ontology, but it absolutely is essential, though. If we're going to make probabilistically qualified statements, so I have to ask, well, what does that mean? And in the context, and that's true both in classical and quantum mechanics. We have to make sense of what it is to ascribe a probability to a certain event. But I think it's a misleading way to talk about a shift in ontology. I think is very, very misleading.
Yeah, I mean, the only thing I'd say qualify that is, I mean, I think people use ontology in narrower and broader senses. I like the narrow way of using it as it happens, but somewhat terminological. I think I could probably rephrase the question as something like we want to clear ontology and ideology, and probability is there foundationally in Gibbsian statistical mechanics. And the ideology here is not fully clear. It's not clear what that concept is. And explicating that concept clearly is, I think, part of what people have in mind sometimes when they say there's problem of ontology. And of course, in quantum mechanics, where the probability distribution goes over to the quantum wave function, then even working out quite what side of the line to put it on starts being blurry, or at least contested.
Yeah, thank you. There's a lot, very much a great part of what you're saying I agree with. And that deals particularly because I think, just like you, that the Gibbs framework has been the dominant framework in 20th century and probably also in future statistical mechanics, much more than the Gibbsian framework, where much more than the Boltzmannian framework, where particularly that framework that Wendell and Frick call the Boltzmannian frame. The only exception probably is when it comes to equilibration, in which case something like a Boltzmann equation seems to be much more the dominant view in statistical physics. But I want to resist the idea that there is no ontological difference between the theories. In both, and so I also have some sympathy with their complaints, not about their complaints about the averaging principle, because I think that's a bit silly. But look, the Gibbsian approach, as you describe it, is it's more or less abstract formalism. So you have statistical state, you have a set of observables, you have a canonical distribution, you have some recipes, but what's lacking, as far as I understood or heard, is a connection with what happens in the laboratory. There has to be some, at least even empiric, there has to be some connection, empirical interpretation rules before we can say even whether this formalism is empirically adequate. And in Boltzmann's framework, that is never very much of a problem. But in the Gibbsians, especially if you focus on the canonical distribution, as you said before, I mean, there's some quantities that you relate with just functions of phase space. There are others, like entropy and temperature, that are associated with parameters in the canonical distribution, or functionals of the. They're not functions on phase space.
Yeah.
And so if you have one particular system in your lab, which consists of a finite number of molecules, and they have microscopic variables, you would assume, like Boltzmann did, that it is presumably described by some microstate in phase space. That's the most.
I wouldn't actually, but I can see it's a reasonable thing to say.
And now, if you use the Gibbsian framework of temperature, you would say, if you would ask this somebody working in the lab, what's the temperature of this system? If you are a strict Gibbsian, you would have to say, well, that's just a functional in the canonical distribution. And so you would ask, well, what is its distribution? Well, it's a property of the ensemble. You can't read off the ensemble from the single microstate in your lab. You first have to decide whether the system is in equilibrium or not. And even then, there's little information about how you could go about experimentally measuring this functional in your ensemble. And something similar can be said about entropy. There's no observable, there's no phase space function that represents entropy or temperature compared to the Gibbsian framework. So there's, and I think that in your conclusion, you said it determines the probability over, and so the expectation value of any variables of the system.
Yeah, I should be careful there.
Yeah, but that's not temperature, not the temperature, and not the entropy. So there are some lacuna there that have to be filled, I think, to be quite as categorical as your conclusion is.
Good. Okay, there's a lot there. Let me go in order. So the first thing I'd say is I want to push back a little bit on the comment about equilibration. I mean, if I look at non-equilibrium statistical mechanics, I'd say most of that is again done in Gibbsian technology. Even the Boltzmann equation, the technology that's being used to study that in modern non-equilibrium stat mech is mostly, I think, more naturally understood on the Gibbsian route. It's either, I can either derive the Boltzmann equation or its generalizations from BBTKY, or I can derive it from something like Myrvold, and both of those frameworks are formulated at a Gibbsian starting point. And if you look at the more recent kind of quantum stuff on equilibration, I look at things like the eigenstate thermalization hypothesis, that's explicitly Gibbsian in its character. So I want to say, like, I think there's more to be said, at least, about the question how to think about the non-equilibrium side of the story. As far as the measurement theory is concerned, so yeah, I mean, point taken, of course. It's certainly true that we do it. So, okay, so I don't think there's a problem. If we're talking about measuring mechanical variables, I don't think it's a problem that the predictions are probabilistic. We know how to deal with it. If my I mean, my theory, quantum mechanics make probabilistical predictions. We know how to test theories and make probabilistic predictions. I agree the story has to be considerably subtler for quantities like temperature or entropy. I mean, the cheap thing to say about temperature is that I think that the microcanonical temperature is a state function and the canonical temperature is an expectation value of that. But even the microcanonical, it's worth saying, even the micro, and that's relevant for the Boltzmann position as well, even the microcanonical temperature, which is the rate of change of the energy height, as you know, is the rate of change of log the energy height, 1 over the rate of change of log the energy hypersurface with energy. Even that, while it is technically a function of microstates, is the kind of horrendously indirect function of microstates that you clearly have the hope in hell of measuring just by some direct quick look at the system, unless you've already got a lookup. So if you look at how we actually go about measuring something like temperature, I mean, just in crude generalization, how do I measure temperature thermometer? What I do is I take some other system with a known equation of state such that some mechanically measurable quantity varies in a known way with respect to temperature. I allow it to reach equilibrium, and then I measure that quantity. And in doing that, I gain statistical information about the ensemble, which in macro-sized systems is de facto certain, and for micro-sized systems would require a somewhat careful analysis. My guess is that the way you'd throw it, you probably have to put some sort of Bayesian distribution over initial ensembles and update on the basis of the data. So I don't think, I mean, it's notable these things aren't inaccessible, and we can make fairly clear sense of the operations we do, but there's certainly a subtlety as to what quantity they're measuring. And I think it's worth saying that as far as I know, temperature fluctuations are not the kind of thing, in the canonical temperature fluctuation sense, are not the kind of thing anyone's trying to measure, or even that are obviously that meaningful in these microsystems. So if it turns out that temperature tends only to be empirically accessible for large systems and needs to be thought about in a more theoretical way for small systems, I'm pretty relaxed about that.
Basically, I was going to say something very similar to what David said. I mean, I agree there is a lacuna there, but I think it can be filled. I've got a paper which is planned to be a chapter of a book I'm writing on the Phil Sky archive called "On the Relation of the Laws of Thermodynamics and Statistical Mechanics," and I've got a section addressing that to people who are worried about entropy and temperature being parameters of a probability distribution. And the way to address that is, think about what the operations we actually call a measurement of temperature or of entropy. And for large systems in which the canonical distribution will be very tightly focused around certain the expectation values of things, then you show that the measured value, what you call a measurement temperature, will almost certainly be 1 over beta.
Sure. But it's going to be slightly more complicated ontology than what it boils down to is the system itself does not have temperature. The temperature is almost by definition a quantity of the system in which your system is in equilibrium.
No, I want to resist that. I mean, well, let's do an explicitly quantum example by analog. I mean, if I take I take some quantum system and that's entangled, and I ask, like, how entangled is it? And we have metrics for entanglement. It's a perfectly meaningful scientific question. There's also no self-adjoint operator that we can measure on the system that returns the level of entanglement. So the process of testing whether a system is entangled and of quantifying its entanglement is indirect, complicated, might not give us reliable answers in any direct empirical context. Nonetheless, I want to resist the idea that entanglement of a system is necessarily a property of a system to which I couple it. And I think, I mean, say again? It's a property of state, yeah. So then the entropy is likewise, and temperature are likewise going to be properties of the state in statistical mechanics. Now, then that's going to, how you want to think about the metaphysics there is going to depend on how you read that state. Since I think statistical mechanical states are literally quantum states, I'm going to say and in fact the that metric of entanglement is literally the entropy we're discussing here, I'm happy to say that to the same degree that entanglement is a property of the actual quantum state of the system, and therefore of the actual system, then so is temperature. But I can see that if you either have a less scientific reading of quantum mechanics or don't buy my quantum imperialist line on statistical mechanical probabilities, then there might be a different line one might want to take.
Patricia, question? Oh, you had no question? Okay, any other questions? Feel like the
Eddie has a question.
Oh, Eddie? Oh, yeah.
Thank you, David. So set aside the equilibration, how to define entropy and error of time issues. The Gibbsian system mechanics for this part of system mechanics seems intertranslatable to the Boltzmannian system mechanics, given you have different versions of the radical typicality version, the pluralistic typicality version, which is the Boltzmannian system mechanics with probability distributions, right? Because they are part of the same mathematical theory, but with different ontological or physical interpretations. So in this part, doesn't seem to be much mathematical difference in how one ought to do system mechanics. Doesn't seem to be much difference in terms of applicability. The only difference seems to be, should we think about system mechanics as primarily about the statistical states or the physical state, but our knowledge of it is not very sharp. So is there any fundamental difference in how we should think about the interpretation of StatMech in this domain?
So I think if you look at originally what is being claimed about Boltzmannian statistical mechanics, it's being advanced as a relative, if you look at sort of the way Goldstein or Leibowitz or someone writes about it in the 90s, it's being claimed as a sort of radical correction to lots of profound confusion and mistakes in statistical mechanics. It's rejecting, it's pushing back against the whole ensemble idea, it's pushing back against the use of probability arguments in explaining particular framework, it's pushing back against the Landau-Bennett kind of idea. I think there's if your notion of what Boltzmannian statistical mechanics means is so capacious that that it can extend to saying, suppose I have a macroscopically large quantity of identically prepared systems, and then I can define on those things a formal object which for typical systems will have this value and which will determine the statistics of all measurements made on that system. At that point, while I haven't necessarily got a problem with that, or not one that I'm stating here, then I think this has faded away as a distinctive set of claims in philosophy of statistical mechanics. And I don't think much is left of it other than a certain theory of probability. I think that theory of probability is false, but for reasons independent of that framework. But I think there's a radical redefining of the goal here that I think needs to be made clear. It's an enormously more modest project if that's intended. It just becomes a claim that it's at some rather general level that typicality is an adequate grounds for probability claims.
I mean, I'd like to defend typicality more, but I was thinking two small things here. First, I don't think that the Boltzmannians who like typicality, who like in the Rutgers school, really identify typicality measure as strict frequency, derived from frequency. There's
no, that's not what I mean. Sorry, just to make
okay.
I mean the opposite. So I'm claiming that an extremely robust and non-extremal notion of probability for individual micro and mesoscale systems is scientifically essential. And if you're not using that notion, you'll simply be unable to reproduce various things. One way you might decide to ground that notion is to say that if I suppose the system I'm looking at, if I suppose that I want to consider the statistics on some large number of identically prepared versions of that, and I suppose that large number is typical in a still larger group from which it's selected, then I can derive that object, and I can derive the claim that typically I will observe statistics given by this function. But that just seems to me to be a version of a quasi-frequentist approach to philosophy of probability. It's not even necessary. I don't think it's the correct version for reasons totally disconnected from this. But I'm sort of, if that's all people want to mean by Boltzmannianism these days, that's fine. But it's really different from what's meant previously.
So I do think that the focus in those arguments, kind of polemic arguments against Gibbsian system mechanics, were more focused on Boltzmann entropy and times arrows. But I see that you're quite worried about the quasi-frequentism But there are, I mean, this seems to touch on foundations of probability too. How do we understand probability measures, and how do you understand typicality measures? Can they be understood independent of pure frequencies? There's something theoretical going on here. If one has a, say, statistical account of typicality or probabilities, then the distinction becomes much less sharp, because you can have, frequencies as a guide or some kind of ingredient in constructing the theory for the probability measure or typicality measures.
Yeah, but I think the reason the distinctions become less sharp because the goalposts were shifted, if you don't mind the mixed metaphor. I mean, there's a Boltzmannian position that's supposed to be, physics salient, supposed to actually be relevant to the way in which we proceed and model and do statistical mechanics. It was a position that wanted to argue for, deep confusion and error in this kind of practice. It's invisible to, for instance, testing the Leszczynski equality, whether the thing that is being tested, whether the probability measure that is probability distribution that is being measured is to be understood as an objectified credence or epistemic chance, is your phrase, isn't it? Or as something a frequency derived from a typicality measure, or a quantum mechanical probability in the decoherent limit. It's totally invisible to all of that. I mean, like with entropy, if the argument is something like the notion of entropy we should actually be attributing to individual systems and plugging into thermodynamic calculations should be the Boltzmannian notion because the Gibbsian notion is incoherent, that's a substantive, interesting, radical, and scientifically inadequate thesis. If the theory is simply something like, of course, the number we should be plugging into these things is the Gibbs entropy, but by the way, the reason for that is we should consider our system to be a member of a typical sequence selected from a vast ensemble, and on that vast ensemble, entropy is log s. Again, that's a radically different and more modest claim than the previous one. And not necessarily, I don't really have a problem. I mean, I do have a problem, but internal to this talk, I have no problem with best system style, typicality style arguments for what these probabilities are. That's an interesting philosophical thesis. I'm a philosopher at least half the time. I care about interesting philosophical theses, but it's not the thesis started with.
Thanks.
Yeah, thanks. So just following up on this exchange. So yeah, I also want to just flag, as I think Eddie was saying, that you don't have to understand these typicality approaches in terms of frequencies, actual or hypothetical. I think I see your point about moving the goalposts. So let me say how I'm understanding that and tell me if I've got it right. Yeah. So some typicality people think like you don't need probability at all. You could sort of, it's kind of like a course correct. It's like, well, any probability measure, almost any probability measure that's like not a super bizarro one is going to give you the right statistics over certain sorts of experiments. And so I don't want to commit to there being like a real thing in the world that probability measure represents. I just want to commit to the like typicality claims that large class of probability measures can do. So that would be one goal that you could have, and to do all of StatMech under that constraint that you're imposing on yourself. And then another goal would be I'm totally fine with thinking the probability is representing something physically real, and thinking there are many different things in the world. It could be representing credences or chances or whatever. But also thinking that there's some story about how that probability arises, and that's where typicality would come in to like give us that story. Is that the kind of goalpost shifting?
Not entirely. I mean, okay. It's not completely disconnected, but I mean, let me first say something to your previous comment. So, I get annoyed when I get called a wave function realist, but being called that by people who don't think the wave function describes physical features of the system at all is kind of understandable. They're conflating distinct views that they think are all similar from their perspective. I'm conflating their system style accounts with frequentism.
Sure.
Right?
Okay.
That's a sin. I should be more careful. That's what's going on there. I'm talking about approaches to probability of that general character. There are categorical features of the world that are somehow supposed to underlie these things. And I appreciate the best systems analysis is not literal frequentism. This has a significant family resemblance to it. But in terms of the more substantial point, I think the way you've hashed it out makes it sound like a distinction within philosophy of probability. I guess my point is that the initial Boltzmannian thesis wasn't a philosophy of probability thesis at all. It was a much more sharp, sharp in the aggressive sense, stated objection to the way statistical mechanics was being done, taught, explained, thought about. If the only difference between if the only difference between what I'm saying is that the things I'm talking as probabilities are things that I think should be explained a la Wayne or a la quantum states, and the view that they should be thought about as ultimately coming out of typicality. It's just impossible to read the kind of things that were being said by Boltzmann and Leibowitz and Craig Callender about the Boltzmannian position in the late 1920s on that basis. They're clearly not saying that just as a matter of the literature. They're clearly saying something that's committed to a different take on statistical mechanics. It's a take that says something like equilibration is associated with the system reaching these values. It's associated with a dominant region in phase space. Putting probability distributions over phase space is just misguided. It doesn't make sense to think of these kind of informational conceptions of entropy. It doesn't make sense to think about in the most formal way of the entropy as rho log rho. That position is a sharp, clear statement that was extensively discussed in the philosophy of statistical mechanics in the 1920s, and is absolutely in conflict with things I'm saying at the moment. That's a meaningful conflict. I don't necessarily want to get into the hearts of the extent to which people really meant something else or it shifted, but in any case, in terms of the public understanding of the framework, there is a big difference between the way these ideas were being explained there and the sort of way one might reconcile the enormously extensive use of probability in StatMech with typicality notions as a philosophy of probability matter.
I see. Yeah. So I was kind of parroting back stuff Shelley Goldstein often says, who's of course working from Joel Leibowitz, but might have a different spin on it. So you're thinking more of the Joel Leibowitz line about how to think about these probability measures.
Yeah, but I mean, look, in a certain sense, this doesn't matter. But go back and look at what is being written about these ideas in the 90s and look at how you just interpret that directly and see the degree of change. I think I need to see what Wayne thinks, actually, but to me, I see a rather radical change in the position.
Yeah, we're going to come back to this in the roundtable. The topic is going to be, is in fact there a schism between Boltzmannian and Gibbsian statistical mechanics, and if so, what actually is the distinction? Because there is something like it is certainly true, as David said, that in the late 90s and the early 2000s, we started seeing these polemics emanating from Rutgers against Gibbsian, the Gibbsian, right? And but when you really press Shelley, he sounds a lot less strident, a lot less dogmatic than he sounds in some of these polemics. And I mean, I've seen him give a talk several times where he's got these overhead slides where he's got good words and bad words, and the bad words are ensemble, etc. And then on the bottom of one slide was what are good Gibbsian methods good for making a connection with thermodynamics, but he never gets around to telling you in the talk, telling you how that worked. And a couple of years ago, I wrote up, here's how I think you get thermodynamics from statistical mechanics, and it's basically the thing that's in that paper I mentioned on the PhilSci archive, and I sent it to a bunch of people, including Shelley and David Albert, other arch Boltzmannians, and he said, is this okay? And I asked Shelley directly, is this too Gibbsian? He said, no, that's not too Gibbsian. So what exactly is there actually substantive disagreement, or is a difference in emphasis? It's not really clear to me.
Or is there a shift in the position?
Or is there? Yeah,
is that acknowledged?
Shelley, a few years ago, has that article in the Monist about ensemblist versus individualist approach to statistical mechanics, and there's this wonderful phrase in there. He says the distinction between Gibbsian and Boltzmannian statistical mechanics has been overemphasized, and I love the passive, and I love the passive voice of that. He doesn't tell us who has overemphasized that.
Yeah, I mean, all I can say really is that if you are going to be very polemical at length in places that are highly influential, don't complain when people criticize that polemically stated view that really meant something different.